people. I just did 1-8 on Wednesday. All right, now, good.
You got a question?
Are we still gonna have a quiz on Friday? After
No,
Wednesday?
no. The quiz is next Wednesday.
I mean, but like, after, like, so next
Maybe,
Wednesday, next
maybe,
Friday will be?
Maybe, depending on how I feel. All right, now, questions about the homework? Yes, sir. Yes, sir. 2.51. Somebody asked me, are you going to be using this book the whole time? I'm going to be using a lot of different books to draw problems on, all right? Not just this one. So, yes, sir. You got to speak up. Guys, quiet down. What? Hey, come on. I can't hear you.
I didn't see the solutions.
How many have seen the solutions? What are you looking at? On OneNote, or are you looking at? I sent an email to you with 2 PDFs.
Yeah,
Both PDFs have the yes. Somebody sent me. They didn't have from 53 on, right? And so I made it a point to copy that and email it out to everybody. All right? And I put it in there. You should have them, sir. You just double check. They're there.
I only saw the 2.6 one, so I didn't see it. I'll check it.
They're all there. I'm certain. If you're, what's that?
I said it was just out of order. That's good people are at the bottom.
All right. Now back to what problem was it?
2.58.
Okay. Work with me on this one, guys. That's a good problem. Slide 2. All right. Now we're going to use Kirchhoff's current laws to find this is going to be done with loop or mesh analysis, or mesh analysis. So, very first thing, by inspection, can everybody see that I1 is defined already as 4 milliamps, just by inspection? Can you all see that?
Yeah.
Class?
Yes.
Everybody's got that, right? That's 4 milliamps just by inspection. Take one look at that. Look around here. This submesh, here's where it's only I1. It's 4 milliamps. Got it, class?
Yeah.
Now, the next thing we have to do is sum voltages around the closed loops. And I always recommend you start at the lower left-hand corner of each one of these submeshes. This is a submesh, this is a submesh, this is a submesh, this is the whole mesh. So I'm going to start right here. And why don't I start here and go around? Somebody. Well, we know I1, but you can't sum voltages through a round of a loop with a current source because you don't know what this voltage is. And it's a source. And besides that, we've got I1, so we don't do that submesh. So we start right here, and the way I always do it, I go around this way and I take all the voltage drops on resistors as losses or as decreases, meaning I want the net current entering the positive, leaving the negative of that resistor, all right? Going in a clockwise direction. Start down here. First, are these all 1K? I didn't put in a value. Is that 1K, class?
Question.
What, huh?
In the book, it has I1 at the top and then I2 and
Fine,
I2 at the
we'll
bottom.
put I1 here.
I'm just curious.
I don't care what you call it. I2 here. It doesn't matter which number.
It also has I2 in the
Fine.
you just
We'll make it any way you want. Make that I3. It doesn't matter. It doesn't matter. You can put any letter you want. You can put A, B, C if you want. All right, it doesn't matter. Anyway, getting back to this, we'll do it this way. That means this is I3. You never have to worry about that. Those are just arbitrary symbols. You don't have to put I1 in a certain place. All right. Now, moving on with this, I'm going to start here taking them all as drops with this convention for currents now, okay? So when I do that, I start here, I get a drop. By the way, are these all 1K resistors?
Yes.
Thank you. Which makes this problem pretty easy. So starting here, I got minus 1K, and if I don't put the ohms next to the K, it's implied. Everybody got that? It's implied. So I have minus 1K. The net current flowing in this direction is what, class? I2 minus I3. I know my handwriting is bad, but then I go here, right? Now I come here, and I want them as drops, right? So I'm going to take minus 1K, that's the resistance. What's the net current flowing in this direction, people?
I2 minus I1.
Right, I2 minus I1. And finally, I come here, I go from here to here, there's a voltage. Did I increase my voltage here or decrease it? Drop it, minus 12, right? So it's minus 12 equals 0. Now, before I continue, I know I'm going to knock off the negative signs, just listen to this. What I'm going to do is replace I3 there, where I3 is there, with the actual value of 4 milliamps, okay? Everybody see that? All right, so I'm going to replace I3 with 4 milliamps. Now, some of you know me. How about I get rid of the negative signs next? Okay? Multiply both sides by minus 1. Gets rid of that. Makes that a plus. Makes that a plus. Everybody agree with that? This is just organizing data so you can put it into your calculator. That's all it is. Or use Kramer's rule. Now the next thing I'm going to do is take the 12 to the other side. Agreed, class? 12 to the other side makes that negative on the other side. No magic here. Now the next thing I'm going to do is divide by 1,000, or divide by K. Understand, everyone? Can you guys in the far back see that? I can't tell. Can you all see it back there? Can you see this okay? I gotta make sure. You can? Okay. Give me a thumbs up, can you? Okay. Far back. All right, gotta make sure, because I don't know how you can. I can, from back there. I'm gonna divide by K. Now this makes this 12 milliamps, right? Now it's 12 milliamps. 1 over 1,000 is milli, correct, class? Now after that, my next thing, I'm gonna take the minus 4 milliamps to this side too. See that minus 4? You all with me? That means I'm gonna add what? 4 to this, right? And that means this will be minus 8 when I'm done, correct, class? So I'll just do that. Agreed? Now, I organize it with I1 first and I2 with the coefficients. So that means this will end up being minus I1, right? Plus 2I2 is equal to minus 8 milliamps. We could multiply it through by a negative sign. Well, at this point, it doesn't matter. That's first equation. Follow me on this? I'm getting it down to a form I can work with. Next, I do it for the upper loop here. And so what I'm going to do for that one, I'm going to start, like I always do, the lower left-hand corner of the mesh is my starting point. This is just my convention. You don't have to start there. But I always do it this way. And if you do things repetitively the same way, I find you make less mistakes. Just me. And I take them with all drops. So I start here, and now I want the voltage drops that way, right? So, starting at this point of going around the loop, I get minus 1K, right? Times, what's the net current flowing in that direction, class? I1. Just I1. Now I'm here, minus 1K. What's the net current flowing in that direction? Class? I1 minus I2. Finally, I'm here. It's minus 1K, right? Times, what's the net current flowing in this direction? I1 minus I3. Good. All equals 0. Agreed? I'm going to, at this point, replace, I on purpose left I3 in there. All right, I didn't put the value in. I wanna make sure you all see this. So when I go ahead and I replace I3 here with 4 milliamps, I have this. Do you agree? Are you with me? Now what's my next step, people? Anyone? Well, I'll get rid of the negatives. We're about to do that too. You can do it all in one step. I'm gonna do it one part at a time so everybody sees this. You got a video recording this. If you don't understand what I said or did, look back at it. Agreed, everyone? Now, I mean, you can do it one step. Now get rid of the K's, right? Now get rid of the K's. Finally, I take the minus 4 milliamps to the other side. Agreed? When I do that, it becomes 4 milliamps. And now we organize the data. I have 2 times I1, right? And I have, or 3I1, pardon me, 3I1, thank you. 3I1, and then I have minus I2 is equal to 4 milliamps. That's my second equation. When you're doing this on a quiz or homework, box the final forms of your equation and label them like 1, 2, follow me? Some way of organizing them. You can do A, B, however you want, just so the grader can see them, can see your logic. Now, put them in terms of a matrix. You'll be amazed at how many people, well, I shouldn't say. I think there are sometimes problems with turning things into matrix forms. I just do. So I'm going to go ahead and take the first equation's coefficients. That's minus 1, 2. Second equation coefficients, that's 3, minus 1. Then I have I1, I2 here equal column vector. The first one is minus 8 milliamps, right? And the second one is 4 milliamps. Now remember, those are milliamps, not amps. Now you can use Kramer's rule if you want to get it, or you can just plug them in your calculators. You're going to get real good at this with your calculators. This is a simple matrix. This is what the thing is. This is the typical AX equal B type problem, and your calculators do this very efficiently. Agreed, everyone? All right, can somebody do this on your calculator? Give me the answer.
Zero, negative 4.
All right, we got I1 is 0, is that right?
Yeah.
I1 0, what is I2? Negative 4. Minus 4, and then I3 we know, right? I3 is defined as 4 milliamps. How many have heard that? How many, I mean, do you all do this? This is a straightforward problem. Hey, listen, don't cut yourself short. Just set up that matrix and say, oh, I got it. Run it in your calculators. You'll be surprised how many people don't know how to operate their calculators right. And you're going to be doing a lot of this, and these aren't going to be just strict real numbers. A lot of the times, you're going to see these coefficients be complex numbers. All right? So you have to be fairly efficient with the entry point, how you enter your stuff. And I wouldn't be anything larger than a 2 by 2. All right? I'm not going to ask you 3 by 3s and things like that. Frankly, they just take too much time to enter. Right? But this is a fair problem. Other questions about the homework? Oh, did I answer your question, whoever asked it? Okay, good. Any other questions about the homework? Yes?
So for this problem, when it comes to the
Go.
I'm sorry. So for this problem, when it comes to the polarity of the resistors, is that
No,
arbitrary?
resistors aren't polarized. This is the polarity of the voltage drop.
Okay.
I always do this, I take everything as a drop through a resistor. That means I need the net current into the terminal I label as plus. You go from a plus to a minus, around summing it's a drop, it's minus. Okay? Yes, sir.
So do you use the equation form V is I times R?
Could you say that again, sir? A little louder?
V is I times
V equals I times R is Ohm's law, yes. That's right. It is. Is there a question?
No, I was wondering how when you turn the all these lines and stuff.
V is I times R, that's basic Ohm's law, and because we're looking at voltage drops around a closed loop, we're always taking the resistance that the current flows in through times the net current to get the voltage drop. Okay? All right, yes, sir.
You're saying we know I3 because of the 4 milliamp input, but what would happen if that we have an amp input on multiple loops. Would it define both of
Well,
them?
it's even better. If I put this as like 2 milliamps, now you know I won.
Well, I mean, more like if you swap the 4 milliamp for the 1 ohm resistor on the top end by 3, and it has, it's part of both.
That's not a problem. Here, let's do it. Let's put 1K down here. Let's swap that and make it 4 milliamp,
I
right?
meant the resistor below that, so it's
Alright,
intersecting
pardon me?
multiple loops.
Pardon?
I meant to replace the resistor that's between I3 and I1, so it's intersecting multiple loops.
Right here?
Yes.
Okay, that's not a problem.
Okay.
Resistor here. Take that out, put it in a current supply, right? And let's say this is 4 milliamps, right?
So do you have to use
Now,
nodal then because it
huh?
splits?
Pardon?
Do you have to use nodal analysis then because it splits between I3 and I1?
No. But here's the thing, right? When you do this one, you're going to say that if you take this is I1 and this is I2. I'm just saying, call this I2, that I1, make this I3. What do you really say? Right here, what happens? That 4 milliamps is what? That's equal to I1 minus I2, isn't it? That's how you do it. I1 minus I2. Isn't that right, class? It's the net current flowing that way is I1 minus I2. That's all you need to do. I mean, sometimes it's not just one thing to find. But that's a good question, I'll say that. Any other questions? No. All right. Now we're going to be talking about another technique. Yes. Speak up too.
Hey, how do you define the current, like positive to negative? Like you change it from one little mesh to another one. How do you know which one?
I think what you're really getting at is how did I know to assign this a plus and this is minus for the voltage drop?
Yeah.
The essence is this. I always want to get drops or decreases in voltage around a circuit if I have resistors. If I have a voltage, I already know what its drop is, right? Or its increase. So when I do this, if I put plus to minus this voltage, VR here, well, what is that voltage? It's the net current flowing that way, isn't it? The net current flowing that way would be I1. So this voltage drop would be I1 times 1K, and the sense would be negative because it goes from plus to minus. Do y'all see that? So when I go around the loop, when I'm summing them, that would be a minus 1K times I1. All right? Follow me on this, everyone? Yeah. All right. Now, we've done nodal analysis, right? That's where basically for nodal we assign currents and then unknown voltages and we solve for the voltages, right? That was nodal. Now we did mesh or loop analysis. There we assign unknown currents and we solve for them by doing voltage drops around closed loops. The other one was Kirchhoff's current law. Some of the currents into the node was 0, or some of the currents into equal to some of the currents out of. We'll solve for voltages. Here, some of the voltages around any closed loop was 0, and we solve for the currents. Now we're going to do a technique called superposition. And this is another analysis technique. It works. And I'm sure there's parallels in your aeronautical engineering and mechanical engineering and probably just about all engineering, industrial. I'm not certain, but I think there are for this. So, here's the next thing we do. This is called superposition. It really just is using the basis of linear circuit analysis. For any linear system, you can do it. All right, let me give you an example how to use superposition. Suppose I have a voltage source here. Call it V1. I'm going to put a resistor here, R1. Another resistor here, R2. Another resistor here, R3. And then another voltage here. Call it plus to minus V2. And I want to find the voltage plus to minus across V2. This is what I'm after. So V, call it VR2, or V, maybe just VR for now, VR. I'm after that voltage. Now you could get it by nodal or mesh, correct class? Those two techniques would get this very quick. But using superposition, what it says you do is this. It says you really just turn on one source on one source at a time. And find output. And then what you do is, with second source, with second, third, etc. sources, you turn them off. Now what do I mean by that? It means if it's a voltage source, you replace it with a short circuit. I'll get out of the way and I'll explain this. With a current source, you replace it with an open circuit. I'll do examples of that. And here's really what you do. If I want the voltage here, I start with this source, call it V1. I turn this source off, I make it a short circuit. Got it? Then I solve for this voltage. Follow me? Next, I record that voltage that I got there. I turn this circuit off, make it a short circuit because it's a voltage source. I energize this one, and I find the voltage here. Then I add those two voltages together, and it will be the actual voltage that occurs there. This is called superposition. It's a useful technique when you got really wacky looking circuits. All right, because you basically just use one source at a time to find the output at that point, and turn all the other sources off. Then you turn the next source on, turn all the other ones off, see what the output is, and go through the thing, turn them all on, and turn off the ones that aren't being used. Find out what the output is there, then add up those outputs. That is the output. That's superposition. Yes? Turn them off.
No, but before the second, third, the width. He's asking about the width. With second, third source.
Oh yeah, you turn off the sources. All right. Second, third, etc. sources turned off. Turn them off. Let me give you an example. When I say turn them off, voltage becomes short circuits, current become open circuits. Got it? If I do an example, this should bring it to life, I hope. All right, so I'm going to put an example down, we're going to work it. Yes?
Can you just give like a quick, like 1-2 second explanation of
Short circuit is 0 ohms. It means, think about this. Put a screwdriver across a battery. That's a short circuit, car battery. That's what it means. There's 0 resistance. Open circuit, no current can flow. Open circuit, cut the wire, you got an open circuit. All right, now I'm going to show you how this works. We're going to do some problems because my belief is this: with circuits and many other things in engineering, the way you appreciate and understand the concept is applying it and solving problems with it. You generally don't speak about incompressible fluid dynamics in terms of a long paragraph and then expect kids to use that theory to solve problems, because until it's applied, you don't understand. You got to see the mathematical application. So we're going to do one. As a matter of fact, we'll do one out of the book, because the guy who created this is probably the single best circuits teacher in the world. His name is Dr. David Irwin. He's upstairs, and he's been here a long time. He's probably taught your parents or grandparents, but he's one of the best. All right, so I'm going to do 2.63 using superposition. And by the way, you can use any technique to solve any of these problems, which is really nice. Any technique. So for this one, you have this. You have 2 k ohms here. You have a source here, and that's 2 milliamps. And then you have 2 k ohms here. Then you have 4 k ohms here. And then you have 4 milliamps here. That's the problem. And they want this current. They want the current through the 4K. That's the current they want. So we're going to use superposition to solve this, and we're going to do it efficiently. And what the nice thing about superposition is, if you want to do part of the analysis with nodal using superposition and so on. So here's what we do. I'm going to call this source 1 and call this source 2, all right? Follow me? That's source 1, that's source 2. Now I'm going to allow that source to stay on. So I'm going to have the 2K here. I'm going to have the source 2 milliamps here. All right. Then I'm going to have, that's going to be 2K here. That's 4K. I want this current, this is my output. I'm just going to call it I out for now. And this one becomes an open circuit. You see how I turned off the second source? I literally made it an open circuit because it's a current source. How many can see this? Follow me what I'm doing? I literally cut it out, didn't I? I ripped it out. Now, I want to find this current. Now, I want you to watch this and you'll see it very easily. When I do this, can you see the 2 and the 4K are in series? Does everybody see that? They're in parallel with that 2K. So really what I have is this. I've got 2K here. I have a current here equal to 2 milliamps. Then I have a net resistance of 6K, and I'm after this current, I naught, right there. Everybody agree that's a reduced version of the circuit, guys? Can you see it in the far back? Everybody agree? Far back? You got that? Okay. I don't know what you're trying to say. All right, I'm after this. Now, isn't this the ideal for current division? If there ever was a time to use it, this is it, right? I can say that that current is equal to the net current flowing into this node, right? Which is 2 milliamps, right? 2 milliamps. And then you take the opposite resistance, 2K, over the sum of this plus this, or 8K. Y'all see what I'm up to? And what does that give you? Well, that's 4, I mean, K's cancel. So I got 4 over 8, don't I, class? Or I have 1/2 milliamp, and that would be for the first, this is from source 1. Agree with me? Do y'all agree with me? Give me a show of hands here. Here's something else. When you think about resistors in parallel, current always takes the path of least resistance. The more resistance, the less of that current goes to it. As this thing gets to infinity, no current at all flows through it. Follow me? Yes. What? Oh, you want to pick? Y'all with me on that, class? And by the way, this is a video online, so you don't need to take snapshots all the time unless you want.
Why is it 2K over 8K again?
Remember, it's the opposite resistance, right? Over the sum of the two. All right, over the sum of the two. Got that, everyone? All right, so now we get this, we do it again, but this time we turn off this source. I'm going to do it right here. Can you all see this? So now I turn off this source, right? What does it become?
Open.
Open circuit, right? It's a current source. Open circuit, you just erase it. Doesn't exist, right? Now I want to find that current. Correct, class? I want you to follow me on this one. Y'all see what I'm doing? We lit up that second source now, right? We turned off the first source. Everybody see this, please just bear with me. I'm trying to make a point here. Now, what do you see about these two resistors? They are in, and the net is 4K. So couldn't I just do this and make this 4K? Right? Agreed? Well, common sense tells you if they're identical resistors across the same voltage, they better have identical currents, right? How many see that exactly half of that 4 milliamps goes to that 4K? Right? But just for the record, I4K, right there, or I out, would be equal to the net current 4 milliamps times the opposite resistor 4K over the sum of the two, which is 8K, right? And that's exactly 2 milliamps, right? So that's 2 milliamps. Which means the net output, now my total, the actual value for I out, or I4K, would be 1/2 milliamp plus 2 milliamps, or it's simply going to be 2.5 milliamps would be the answer using superposition. Do you appreciate what I'm doing here? I'm going to do one with a voltage. How many see this right here? This is superposition. The nice thing about it is most of the time, you don't need anything more than series parallel combinations that you have to take care of. Yes, sir?
So why did you put a different I naught for, both of those two?
Well, one is from the first source, the other is from the second, right? There were two different sources, huh?
And then you just add them together?
Yeah, add the output.
And then what did you say the equation was again for like the superposition equation?
You mean current division? Is that what you're talking about? There is no equation for superposition.
Oh.
What? It's a
What's
tech.
current division?
If you have two resistors, R1 and R2, and you wanted the current through this, I2, if there's a net current flowing into it of I0, the current through I2 would be equal to that value I0 times the opposite resistor over the sum of the two. That's current division. We covered that a couple lectures ago. Y'all remember this? Right? Can you see it? Can you see what I wrote
Yeah,
there?
I can see it, yeah.
That's current. Go ahead.
What is the one that's like I2, or the I equals I1 plus I2?
That's Kirchhoff's current law. It's the sum of the currents into a node are equal to the currents leaving the node. Alright?
Oh, so anything different about this is that it's.
This isn't anything to do with, this has to do with the actual division of currents. How much of the original current divides between two parallel resistors. Alright, now let me do another one. Hopefully you'll appreciate this. Hey, have you watched these videos at all, anybody? How many have? So, are they good? Good quality? No? Yes, I could. It's hard for me to, I'm trying to listen out here, there's a lot of mumbling, and so I hear just kind of bits and pieces. All right, next, here's a cool one. Let's do this one. This is going to be 267, 2.67. So, all right, here we have two different sources, a voltage and a current source. And what's looked for is not current, but the voltage across this 3K measured plus to minus. Follow me? We're going to use superposition to solve this. We can use any technique we care to, but in this case, we're going to use superposition. So what I'm going to do is call this source 1 and this source 2, okay? Got me on this, everyone? Now, to start with, I leave source 1 in there. So I have my 6 milliamps there. I've got the 6K down here. I've got 3K down here. But, let me just do this. Here's where the source is, right? I want everybody to watch this. Now, I call this source 1, so I leave that one in there, but this is source 2, right? I turn it off. I replace it with a short circuit or wire, right? A wire. So just do this. Can you all follow me on this? Right? We want that's 3K, and we want this, plus to minus V0, right? Let's take a look at that for a second. All right, now please take a look, just look at this. And I want to show you something. Take a good look. Some of you see this especially mechanical aerospace engineers, hydraulics people, any people like this usually see this in a heartbeat. When I look at this, and I want to see what's in parallel, I've told you about this before, get different colors if you're curious about this. You have to have the same voltage across them. Use that as one color. Take this as another, start on this side. Now everything that has the blue and the red across it is in parallel. Do you all see that? Then if I have another color, oh my gosh, green. Everything that has green and red across it are in parallel. Can you all see that? Now try to use your mind and your imagination on this one. Can you all see if I took this and bent it, right? I could literally do this. I could bend these two and they would be in parallel, right? And then below them, I could take these two and bend them and they would be in parallel. You all see that? So really what I've got are these two in parallel and these two in parallel. Follow me, everybody? I'm gonna redraw it so you see. So now I've got my 6 milliamps and I'm gonna put that vertical. Here comes these two resistors, right? That resistor is 3K. And there's a plus to minus V naught I gotta find. It's in parallel with 6K right here. Then back here on the other end of this, on that red, between the red and the green, I have 6K and 3K. Y'all agree with me there? How many see this redraw? Go through it later with yourselves. Make sure you do. Make sure you see this. It's a simple redraw. I'm using the technique with colors because long ago I was taught that, and it's the easiest possible way to figure out what's in parallel, what's in series. Everything between the two same colors, between blue and red is in parallel. These two, between red and green is in parallel. That's the way you figure it out. Then you redraw. I always try to redraw them where I'm going down vertically. Everything in parallel is going to be at the same horizontal level. Now, this is in parallel, right? What's the net value of that? 3 times 6 over 3 plus 6? 2, isn't it, class? 2K. Isn't that the same as this, 2K? Agreed? Now, if you have 2K for the parallel equivalent, let me draw that here. So now I'm coming back to that circuit. I have 6 milliamps right there. And now I have 2K here in series with 2K. And this is plus to minus V naught. You all agree with me there? How many see this? Now what's that voltage going to be? By definition, V equals I times R. Do we know I? Yes, right? We know the current. Do we know R? Yes. What is the voltage? You multiply them. Can you all see that this voltage is 2K times 6 milliamps? Or it's what? 12 volts. So is that one, right? That's 12 volts. How many see this? It's not hard to see, but you got to do the redraw right? Now, the next thing I do, so my first answer, or my V from the first source, call it V1, is simply going to be equal to 12 volts. Now I go, and I'm going to do it right here. Now I turn off this source, right? Correct? That was my first source. Correct, class? What do I do when I turn it off? It's a current. What do I do with the currents? Say it. Open. Erase it. Right? Did you have a question, sir? Did you have a question?
Yes. I was asking, why didn't you add those resistors in series to make it 24 instead of 12?
What?
2K resistors?
Yeah, we wanted, see, the output is taken right here. We only want the output voltage across this resistance, right? That 3K is in parallel with this 6K, right? So either the voltage here or here, when they're in parallel, they're replaced by 2K. So that voltage is just going to be 2K times the current, which is, the current's the same in those legs, which is simply 6 milliamps, right?
So when resistors are in parallel, the voltage drop.
voltage is the same across resistors in parallel. The current is the same in resistors in series. All right? The same current must flow through both resistors in series, or any number of resistors in series. The same voltage must be across resistors in parallel. That's the idea. Everybody got that? Spend some time with this. You can easily get swamped with this stuff in the next 5 lectures. You can be so far behind you don't know where to start. All right, so I'm just telling you that as a heads up. So anyway, that's 12 volts. That's our first voltage. Now for this one, we're going to turn off the first source. It's a current source, so it becomes a open circuit. Just erase it. Get it out of there. It does no good. Now this is my source. All right, this is my circuit. Can you all see that? Now I want you to notice this. Please just listen to me. Can you all see that's a voltage source, right? That voltage is across those 2 resistors. Do you all see that? These 2 resistors have the same voltage across it, but they have no impact at all what's over here. Do you all see that? Because the voltage is defined over here. You can put anything you want over here. It's not going to affect that value of V naught. How many see that? You good with it? I mean, I can put it, I can make that 50 ohms, 5,000 k ohms, it doesn't matter. This voltage is the only thing I care about because these 2 are in series. Are they not, class? Do you all see that? And if they're in series, that means that that voltage V out, now we use voltage division, V out is going to be equal to the net voltage. As a matter of fact, just to make the point, you don't need that part of the circuit. You can get rid of that. This is 6 volts. And it's dropped between these 2, isn't it? These are the only 2 resistors that are in series, correct? So if I want the voltage here across the 3K, I take the total voltage, 6 volts. I multiply it by the resistor I want the voltage across, 3K, over the sum of 3K plus 6, or 9K. And now I see that I really have 1/3 times 6, or 2 volts as V out. How many see that right there? Simple voltage division. Do y'all see it, class? Come on, stay with me on this one. I know it may seem too easy and boringly simple, and painfully simple. But remember, I'm telling you this based on teaching this many times. There are courses like it, that people oftentimes miss small points. What was your question? If I come here, now that's the second output. Now I add these 2 together, and my total output would be equal to 2 plus 12, or 14 volts. Do you all see that, class? If you want to try something, go to the original circuit and do the problem using nodal analysis. Make sure you get the same result. You will. Then with mesh, make sure you get the same result. And that way you confirm its validity. Yes?
When you see these problems, how do you know which method will work best or get you?
Now I will tell you, I want you to use loop. I want you to use mesh. I want you to use supervisors. And you better, because if you don't, you get no credit. It's like, the word mesh to me, or loop, means you use that technique, because I test you to make sure you know how to do all of them. All right? I'm just telling you that. All right, now that's superposition. I want to do one other thing too. I want to show you about source transforms, because this is very powerful and useful. And I use it all the time. If you're mechanical engineers or aerospace engineers, not industrial, I can't speak to that with authority, but I can tell you, understanding how you can easily analyze an electric circuit if you've got a motor drive or something like this, or if you've got some reason to have something heated up and you got a power supply, is so important. Because mechanical engineers, electrical engineers, aerospace engineers, they all, believe it or not, work in a realm where they got to understand the other stuff. And electrical has to understand chemistry, has to understand, you know, the heat equations for heat. Heat equals nRT, and not just the ideal gas law, but steam tables. I have to use that all the time. All the things that, this is things we're all going to have in common out there in the real world. All right, now, listen, this is a very useful technique. One of the most useful techniques there is. It makes everything simple. It's called a source transform. All right, it's a bit of a trick. What it is this. If you have something where you have a resistor R in series with a battery V, V naught. And you have two terminals here. You can take this thing and say, you don't have to be that way. What I can do is give between these two terminals, I call it A and B, I can put a current source in parallel with the resistor that'll give me identical outputs for any load. I can say this thing is identical in every way, shape, or form to putting a current source here, where the current I here is equal to V naught over R, with that being R, in parallel with that resistance, R, and then putting the actual terminals. Now, I'm going to show you how come that's so powerful and useful, so you'll appreciate it. I'm going to do problem 272. Please pay attention to this. For this problem, I have a voltage here, 12 volts. I have 2K. I have 2 milliamps. That's milliamps. I have 3K. I have 2K. I have, this is what I want, I naught is what I want. Then I have 3K. And I have minus to plus 24 volts. This is 24 volts. And I'm going to use superposition to calculate I naught. Now, I want you to listen to what I'm saying, and hopefully you'll appreciate it. You see how these two are identical, right? The whole idea is you do these transforms and then absorb an element. Now, you all see here, listen to me, because this is how you add current sources in parallel also, that these two could be replaced by a current source in parallel with that 2K. How many see that right there? You all see it in the back?
Wait, can you point it out one more time?
This and this could be replaced by a current source in parallel with 2K, based on this, right? All right, so the current source would be 12 divided by 2K, or 6 milliamps, right? So it'd be 6 milliamps, it would be flowing up. And the resistance 2K would then be in parallel here. Can you all see that, class? I've just replaced that source with a parallel version. How many can't see this? You understand what I've done way back there? Now, here's the thing. If you have current sources flowing into the same node, you can combine them. This is the same node here, right? Same electrical potential. I've got 6 milliamps going there, 2 milliamps going there. I can add them together and make it 8 milliamps. Do you all see that? Show of hands here. You all see it? You're looking at me suspiciously. Do you see it, miss? You don't. All right. Can you see that that current's flowing in here, right? That current's flowing in here, right? Isn't the net current going in there 2 plus 6? So why make it any more difficult? Just make this 8. Follow me? How many see this now? All right. Same currents going into the same node, add them together, make one current source. Why have 2? Now, what can I do with this? Can't I go back from here to here, right? I can say that this voltage right here is actually equal to I times R, isn't it? Right? I can say this is just equal to I times R. So when I look at this, now I can take the 8 milliamps times 2K and make it 16 volts. Listen to me, right? And then put it in series with the 2K. So I'm going to do it right here, okay? Don't hate me for this. So I'm going to make it 16 volts in series with 2K. Now, why do you suppose I did that? I know you all know it. I'm not trying to tease you, but what can I absorb now and reduce the number of elements? Take one look. How about this 2 and 3K, right? Aren't they in series? Can't we make them 5K? Give me a show of hands. Sure. I'll make that 5K. Now, remember, we want I naught. Here's a lesson. Listen. Don't do anything with that till the end. Don't touch it, all right? You don't, the element you want the voltage or current through, you never absorb. You always allow it to be on its own. That's the last element that we're gonna analyze. Now, do you all see that we could make this into a current source in parallel with the resistance, and we could make this into a current source in parallel with the resistance? Do you all see that? Now listen, I know I'm a little over time. Then I could take the two parallel resistances and combine them. Do you agree with me? Then I would have two resistance with two current sources going into the same node that I could add, and then I could do current division. I know I'm over time, guys, but how many get the idea? I want you to try it. I'm going to give you problems like that for Friday.